So, meeting is being recorded. Great. Thank you, Tony. So as Tony mentioned, I'm Wei Chen. I'm a physical oceanographer from NOAA's Pacific Marine Environmental Lab in Seattle. So I'm one of the co-lead for the PO community of practice. So it is my pleasure to introduce our three speakers today. Dr. Yong Wei is a senior research scientist from University of Washington and also PMEL. Dr. Bretwood Higman, or Hig, is the co-founder of the Ground Truth Alaska, which is a NGO, right? And then Dr. Kristin Timm is a social scientist from University of Alaska Fairbanks. So they will tell us some latest research on tsunami modeling, forecasting, and risk assessment in the Alaskan region. So Yong, and the floor is yours. Thank you all for being here.
Thank you. Let me share my screen first. So can you see?
Yes.
Yeah. Yeah. Good morning, everyone. Thanks, Wei, for the nice introduction. So, really, truly grateful for this opportunity to present our research on tsunami forecasting and hazard assessment, and also to engage with the IARPC community. So I guess everyone knows what tsunami is, but this is this painting is a famous painting titled "Under the Wave of Kanagawa" by a Japanese artist. Tsunami is a Japanese word meaning harbor waves. So calling it a harbor waves may not be very accurate, but it captures the essence of the tsunami. It is relatively quiet in the deep ocean, but it will evolve into monster waves when approaching shoreline or entering harbors. So scientifically, tsunami is a set of ocean gravity waves caused by any large disturbance of the ocean surface that involves all water column in motion. It belongs to the shallow water, or what we call long wave region, not like wind waves that can only disturb the waves on the surface of the ocean. The energy of the tsunami waves is transmitting through the entire water column. So in the deep ocean, these waves can travel at a speed of more than 700 kilometers per hour, like a jet plane, with a wavelength about 200 kilometers. The energy is preserved over the long distance travel in the deep water. And as the water becomes shallower, the energy will be released in forms of like wave height and also momentum force that can penetrate far inland with devastating impact. So tsunamis are mostly generated by large earthquakes, like more than 80%. The rest of 20% can be triggered by landslides, volcanic eruptions, uh, medial events, and also maybe asteroid impact. So the scale of the tsunami problem is both like global and local, and the key points relating to the scale include the source magnitude and intensity, the historic impact, the energy transfer between the disturbance and the ambient water, as well as the warning system. Historically, there are like more than 2,500 tsunamis have been documented since 2000 BC, and every major subduction zone on the Earth can generate tsunamis impacting coastline either locally or globally. These red stars represent more than 60 observable tsunami events since 2004. Within 2 decades of time, the tsunami hazards had resulted in more than 250,000 deaths and $280 billion US dollar damage all over the globe. So this slide highlights the tsunami generated by the Great Alaska Tsunami on March 28th, 1964. It is considered as the most devastating event impacting Alaska and the U.S. coastlines in history. The magnitude of this earthquake is 9.2, rupturing like 800 by 200 kilometer fault in the Prince William Sound. Um, Energy-wise, it is like 40% larger than the 2011 magnitude 9.1 Japan tsunami. Nine lives were lost due to the earthquake shaking, and so the tsunami waves killed 122 people. So the economy loss is equivalent to 2.9 billion US dollars. You know, if you convert it to dollars in 2022. In response to this event, the National Tsunami Warning Center, formerly known as the West Coast and Alaska Tsunami Warning Center, was established in 1967. Uh, this map shows the maximum tsunami amplitude caused by this tsunami and is also a direct representation of the global distribution of tsunami wave energy. So traditionally, the tsunami warning relied on seismic analysis, very limited tide gauge observations, and experience of the warning center staff. This traditional method sometimes can result in false alarms. So in the 1990s, PMEL started to test some prototype of the bottom pressure sensors in deep water for early tsunami detection. This technology matured in early 2000 and fostered the modern forecast system that integrates observations and the model computation in real time for warning and forecast. So during the November 17, 2003 Rat Island event, the tsunami source was for the first time constrained using the measurements from the nearby bottom pressure sensors. The tsunami waves were successfully predicted by computer models 45 minutes before they arrived in Hilo Harbor, Hawaii. So this Red Island tsunami is considered as a proof of concept event for the modern forecasting methodology. So 1 year later, on the Boxing Day of 2004, this Indian Ocean tsunami generated by a magnitude 9.3 earthquake in the Sumatra subduction zone, which is about like 40% larger, the energy-wise, larger than the 1964 Alaska earthquake, killed more than 230,000 people and displaced 1.7 million people across 14 countries. This tragedy was due to the lack of early detection instruments or warning system of any source in the Indian Ocean. During this event, our colleague, actually Vasily Titov, I'm not sure he's online today or not, he made a model prediction based on the preliminary earthquake information, which compared reasonably well with the satellite JSON-1 observation over the ocean surface while the tsunami waves were still propagating. The model results revealed the global impact of tsunami that was observed by many tide stations across different oceans. This awakening event served as the kind of like a catalyst for developing a modern tsunami forecasting system in many countries, including US. So this slide shows the milestones of the evolution of timeline of the modern tsunami forecast that focus on improving speed, accuracy, and the robustness of the warning system in the US. The Congress quickly responded to the 2004 Indian Ocean with the establishment of the Tsunami Warning and Education Act, which is still active, authorizing NOAA to strengthen the tsunami detection, forecast warning, and mitigation programs. By 2008, NOAA has already deployed an array of 39 tsunami buoy stations named DART uh, around the Pacific Basin, Western Atlantic, and the Caribbean. Um, the DART buoys were designed and patented at a PMEL. Up to date, it has been through 4 generations from one direction to directional signal transmitting, easy to deploy, and the latest fourth generation featuring high frequency sampling rates that can separate tsunami signals from the background seismic noise. Presently, the global DART array has grown to a total of 74 sensors, providing real-time early detection and monitoring of tsunami waves. 39 of them are owned by US. Others are through international collaboration. The forecast methodology developed by PMEL was fully tested and validated during the 2011 Japan tsunami. This system, named SIFT as acronym for Short-Term Inundation Forecast of Tsunami, was put into full operation at both tsunami warning centers in 2013. So the tsunami forecast sequence built into SIFT and emphasizes on forecasting of flooding impact induced by tsunami, going steps further than the traditional offshore forecasting. SIFT forecasting starts with the tsunami source estimation using seismic information, the DART data simulation, and also pre-computed model database. The source can then be used for forward modeling to rapidly obtain the basin-wide or global forecast for tsunami propagation. So this forecast can then be used as boundary conditions to conduct inundation computations to predict the tsunami impact for US harbors and the coastlines at risk. There are about 80 inundation forecast models integrated into SIFT across the Pacific, Atlantic, and the Caribbean. As indicated by the green dots in the figures, in Alaska, 17 models cover major harbors and coastal communities at high risks of tsunami hazards. So here I will use the 2011 Japan event to briefly demonstrate the model forecast of the tsunami arrival in Hawaiian Island chain. The inundation forecast models were launched during the event. The model forecast results were obtained about 4 hours before the tsunami arrived in Hawaii Island. These results showed a very good comparison with the observed waveforms at the tide gauges. SIFT also successfully predicted tsunami inundation at Kahului Harbor, which agreed well with the after event survey. We launched a total of 32 forecast models during the Japan event. Here are some comparisons between the model forecast and observations at many tide gauges across the Pacific. These are the Hawaiian Islands and the Pacific Islands, West Coast, and also in Alaska. The red salt line is the model, and the black is the observation. So the forecast accuracy assessed using the maximum tsunami water level recorded at tide gauge is 70% for 32 sites. The accuracy increases to 75% for harbors with tsunami amplitudes greater than 1 meter, and 87% when the tsunami amplitudes exceeded 1.5 meters. So certainly we need to acknowledge that the current warning system is not rapid enough for the near field, particularly for the coastline that are within 60 minutes of the tsunami arrival after earthquake. But the validation study we conduct along Japan's coastline confirms the model accuracy in predicting the waveforms, which is shown on the left, and also the inundation area on the right. Rapid detection of earthquakes and the tsunamis, along with the well-prepared emergency planning and education, are the key to improving tsunami forecasts in the near field. Since 2004, the SIFT tool has been used to monitor, test, and validate in almost every single tsunami event around the world. The colors represent the maximum offshore wave amplitude, which also indicate energy distribution. Alaska remained kind of relatively quiet until 2018, when a series of large and shallow earthquakes with magnitude between 7.6 and 8.2 occurred in the eastern Aleutians and the Gulf of Alaska. The maximum tsunami amplitude recorded was 74 centimeters at the Sandpoint tide gauge produced by the 2020 magnitude 7.6 earthquake located about 100 kilometers southeast of the Sandpoint Harbor. I don't recall this earthquake tsunami events caused significant damages to the local community, coastal community, but I may be wrong. And the tsunami warnings were issued to the nearby residents as well. As I mentioned earlier, the enhancement in early tsunami detection is the key to improving forecasting the near field. So the fourth generation DART features high frequency sampling rates that can separate tsunami signals from the background seismic noise. Comparing to the older generation, the fourth generation DART can be placed much closer to the trench, to the source area. So that can improve the early detection time to the order of like 10 to 30 minutes. The older generation DART could not really detect the tsunami until like an hour or 2 hours later. And also the Global Navigational Satellite System, GNSS, can detect the peak ground displacement from an earthquake within a couple of minutes. In recent years, NASA and NOAA collaborative research has allowed us to implement the GNSS-based rapid earthquake source algorithm named GFAST. We were able to implement GFAST into safety system with sufficient GNSS detection. The GFAST can provide source magnitude estimation in 90 to 120 seconds and a source configuration in 3 minutes of the earthquake. So other technologies that we are looking into include the smart cables, uh, equipped with sensors measuring pressure, acceleration, and also temperature. These smart cables aim for direct early detection of tsunamis for regions not covered by the sparse distribution of the DART buoys. In the meantime, we also collaborate with the colleagues at the NASA JPL to explore the ionospheric detection of earthquakes and tsunamis. The GNSS satellite can rapidly detect the atmospheric waves that produce ionospheric density difference incurred by the earthquakes and the tsunamis, which can be quickly inverted as the total electron content, TEC signatures to characterize the tsunami source for real-time forecasting. In Arctic, tsunamis can be triggered by non-seismic events like volcanic eruptions and the landslides. Alaska is home to over 130 volcanoes and the volcanic fields that have been active within the last 2 million years. 90 of them have been active in the past 10,000 years, and more than 50 have erupted since 1700s. The volcanic eruption can displace a large volume of water, creating powerful waves. Landslides, often caused by the melting ice or unstable slopes, are another significant trigger. This figure on the right shows the documented tsunami events in Alaska and the Arctic, revealing that nearly all tsunami events inside Arctic were triggered by landslides, not earthquakes. The landslides are likely the biggest source of tsunami threats in the Arctic. So we have not done much work on tsunamis generated by volcanic eruption in Alaska. However, it has become increasingly clear in recent years that data from atmospheric and weather observations, when combined with the real-time coastal and deep ocean tsunami detection can provide the necessary input for model forecasts before the non-seismic tsunami impact the coastline. Our proof of concept forecast methodology uh, combines the measurements of the air pressure measurements with real-time tsunami observation to provide model predictions. This approach proved valid, during the Tonga volcanic tsunami that occurred on January 15, 2022 event. The video on the right shows both the propagation of the air pressure wave and also the tsunami waves generated by the volcanic eruptions. So that's why you can see some pressure wave, the air pressure wave propagating over land and then collide on the back of the earth and then coming back to, to propagate like over the globe several times during that event. So these are quick demonstration of the comparisons between the measurements in white and the model results, in red, computed using the air pressure wave as model input for many DART stations across the Pacific. So they all look good throughout the Pacific. So I want to show this slide just because it may somehow be relevant to the ice in the Arctic. The tsunami waves frequently can trigger ice covering events in Antarctica, contributing to the acceleration of sea level rise. The Tonga volcano tsunami triggered the Dragowski ice tongue covering event. The tide gauge at Cape Roberts, approximately 200 kilometers southwest of the ice tongue, recorded distinct tsunami signals. So we simulate the propagation of the land wave-driven tsunami, the pressure wave-driven tsunami um, caused by the Tonga event into Antarctica, as shown in the animation. The model results at Cape Roberts agreed well with the observations. The progression of the tsunami waves at Cape Roberts correlates well with the observation with the ice carving timeline. The carving footage became evident between 1410 and 1550 UTC after arrival of large tsunami amplitudes and intensified with trading waves until the ice tongue completely uh, broke off on the following day. We collaborate with colleagues in Stanford and Scripps to specifically look into the bending force under the ice, when the tsunami waves propagate, underneath the ice. I prepared a couple slides of the landslide generated, but I realized that Hegel was specifically discussed this topic. So he's the expert on this topic. So I will basically skip the sky slides to save some time for Heg. But I would like to give, credit to our colleagues, two colleagues at the Alaska Earthquake Center, like Inena Sonomani and Dimitri Nikolsky for their contributions in inundation mapping of tsunamis, including landslide-generated tsunamis for many communities in Alaska. In these slides, I just want to highlight the tsunami hazard assessment studies we are involving in to enhance the resilience of coastal inundation hazards. Since 2011, PMEL group has significantly contributed to the American Society of Civil Engineers effort to establish national standards for building design in tsunami-prone areas. These standards published in 2016 and adopted by the International Building Codes in 2018. They are the first in the world to address probability-based building resilience to tsunami impact. And tsunami-induced debris is a critical but often overlooked aspect of coastal vulnerability. Our pilot study on tsunami inundation and debris modeling informed a water winging design of the Oregon State University Marine Science Center at Newport, New Oregon, which also functioned as a tsunami evacuation shelter for up to 2,000 people. In recent years, we also focus on, in addition, hazard assessment study based on probabilistic methods, considering the effect of sea level rise. This example shows the impact of sea level rise at Manila, Philippines. When we can include the sea level rise in the model, you can see this amplification of inundation hazards, which is much like about 1 kilometer farther inland than the model with computing without including sea level rise. And besides sea level change, the coastal dynamic process also amplifies tsunami hazards. And this video demonstrates the dynamic process of a sediment transport in the harbor of Crescent City during 2011 Japan tsunami, which scoured up to 6 meters of sediments from the harbor entrance, underscoring a severe but often underestimated aspect of a tsunami hazard assessment. So a few more words on the probabilistic tsunami design maps developed for Alaska that comply with AC standards. The existing inundation maps in Alaska were developed using a deterministic approach. For coastal infrastructures, AC standards require a design to comply with the maximum considered tsunami with a return period of 2,500 years. We collaborate with AC to develop those maps for limited coastlines in Alaska back in 2016, but they were based on a low resolution due to lack of accurate and high resolution DEMs. These maps need to be updated using the latest DEMs and the new logic trees of earthquake probabilities. Washington and Oregon are currently updating all those maps. With this slide, I'd like to conclude my talk today. Our future tsunami focusing on enhancement of tsunami warning and hazard assessment will continue to make a critical contribution towards the ultimate goal of achieving zero casualties in the next tsunami. Thank you.
Thanks so much, Yong. Wow, that's lots of information. With the time limit, maybe we should just move on to the next two presentations and save your questions for the group discussion. Yeah.
Sure.
Okay.
Yeah, I could just jump right in if you want.
Yeah. Thanks.
So yeah, I wanted to talk about landslide-generated tsunamis, and I'm going to start out talking quite a bit and kind of give you a whirlwind tour that will look at the hazard. But I did use the word risk intentionally and kind of understand the distinction. I'm going to try to get it especially into the probabilistic aspect of risk right at the end. So these events where a landslide enters the water and generates a tsunami are fairly common, actually. And most famously, there was this big tsunami in 1958 in Lituya Bay. One that adds a little caveat to Yong's definition for a tsunami, because it was not just a wave, it was also splashes where it reached over 500 meters right here. But there are a lot of other events that people maybe don't know as well. As recently as 2020 and this little lake at the head of Elliott Creek in BC. And I'm going to be looking at BC and Alaska and kind of my tour here. There are definitely some outside these regions too. This one right near Juneau, 1967 Gruink is one that I've worked on a fair bit. I'm going to talk a little more about this event in 2022 in a small lake at the head of Extall River. The event that got me started looking at this, I come from the tsunami world. I worked on the 2004 tsunami. So I've worked on subduction zone tsunamis, like what a lot of what Yong was talking about. And there was, in 2015, in this fjord with a retreating glacier at the head, there was a landslide that came down into the water and ran down the fjord for a little ways. And it generated quite a large tsunami. Highest run up here is 193 meters. And devastated the young forests along this recently exposed fjord. And this I came into it as a tsunami scientist, but this got me started looking at landslides as well, and that's become really the dominant focus of my work in recent years. When you look at an event like this, it's very clear why we're talking about the tsunami. The tsunami is, even if you were to travel there, you could wander around for a while and not notice this quite enormous landslide because the tsunami impacts were so extensive. But there are events where it would be understandable. You might wonder why we're talking about tsunamis. So this is a little pond up at the head of the Extall River. You could imagine if you were camping on the shore of this, you might be worried maybe some rocks will fall into this pond and generate a wave, and it could like splash into my camp and put out my fire or something like that. So in 2022, there was a landslide. It comes off of stage left here. And the toe of the landslide actually extends all the way to here. So it completely sweeps through that lake. If we look at this northern margin of the lake, you'll see how it shifts a bunch, and these are reasonably well aligned. That's because the landslide volume is such that it actually completely displaces that, or completely fills that lake basin, and a new pond forms on top that's tens of meters higher. So I think if you looked at this, you would say, well, this isn't a tsunami story at all. This is a landslide story. There was this huge landslide. Let's go downstream a little bit. So this is a few kilometers down the river. This image from before the event, and some of these I'm using an American football field for scale. And after the event, we see this large area of old growth forest, completely denuded, large rocks moved around. This is entirely the water that did this. And now we could have a debate about what is a tsunami and what is an outburst flood, as one evolve into the other, as a anyway, we could have that whole debate. But the point here is that that water in that lake, even though it seemed like a very small piece of the story at the start, was actually a big piece of extending that hazard downstream. This is another example. This before image, there's a slow landslide basically right in this area, and during a big rain event in August of 2021, it failed. It ran down, banked off the far side of the valley, swept through where these small ponds were, and actually most of the landslide mass is right here. And the tsunami from that completely denuded this large area downhill. So what this is showing is that you can have a landslide in one spot that has a certain extent, but if it hits water, this can extend those impacts. It can broadcast those impacts over a large area. In this case, there was sea ice in this lagoon that was shattered for quite a ways from where the landslide entered, even though the landslide was mostly spent on this glacier. And if we zoom in, we can see that actually it was fairly significant. This is probably pushing 10 meters run up in this area. So definitely would have been a big deal if you were camping in this remote lagoon. If we look through recent history, there have been quite a few of these events. I'm again using Alaska and British Columbia, which is partly just my own regional focus is why I'm cutting it down there. We can split these events into some different categories. These really big ones are all in Lituya Bay. Lituya Bay went through dramatic glacial retreat in the 1600s and 1700s. So it's kind of an unusual glacier schedule and an unusual sequence of landslide-generated tsunamis there. These are a couple of glacier collapse events, very interesting, but maybe they belong in a different category. And I'm also going to just highlight these three that are landslide-generated tsunamis that happened in mountains that had been deglaciated long before the landslide happened. And if I cut out those kind of odd categories, you see this really tight clustering towards the present. And in actuality, this is a little out of date because there's been one tsunami that happened after I made the figure. I couldn't find the graphic file, so I just kind of sketched it in real quick there. So this tight clustering towards the present, I'm not saying there are no gaps back here, but especially when we talk about these largest ones, I think it's actually reasonably complete and that there is really this huge spike in activity in recent times. So I want to go back to this site, as it turns out to be kind of a little more complicated story that's worth exploring. So I stumbled across this image a little over a year ago, and I reached out. There's actually a lodge that's just off the right edge of this screen, and I reached out to them and said, hey, you might want to be thinking about tsunami hazards. We had some really good conversations. They talked about maybe some approaches that could help to mitigate the hazard to some extent. And then on August 6th last summer, I got a call from them and they said, hey, we think it happened. We had some sort of event. And it turned out there had been another landslide tsunami in the same lagoon, and this one was much larger. So these are some of the impacts in the most accessible places that are just up from the lodge. At the lodge, well, I'll show you that in just a moment here. But anyway, so there's some pretty dramatic, like, thrashing of these young alder forests here. About a month later, I went out, and the lodge operations manager was my field assistant, and we surveyed run-ups. These orange flags in both images are kind of our marks for the highest point of run-up. It's really dramatic. It's hard to see in the image because the area is so barren. You can't really see a trace of the tsunami like you can in some cases, but you really feel like you're up on the mountainside when you're standing at the edge of where there's traces of water. And so this is the result of that and some other mapping. Highest run-up was about 62 meters. The lodge is right over at the right edge of this, and so they had probably on the order of 1.5 meters of run-up there, and it damaged docks. It actually swept under occupied guest cabins that were on stilts. So it was a rather close call for them. I think it's also notable that this was a kind of small event to have produced such a large tsunami. As far as the landslide, so here's that 2022 one that I showed earlier. 2024 actually came from a completely different place, which is one interesting thing. And it went onto the glacier, and it traveled quite a distance, almost a kilometer on the glacier, and turned 130 degrees before it entered the water. A lot of things that might lead me to guess that it would have dissipated a lot of its energy. And yet it was able to produce these run-ups of over 50 meters. And I would love to talk about some of the details of what we could do to try to figure out just how much you might expect this. But it's, anyway, that would take too long right now. Very interesting event. So how does a landslide generate a tsunami? Some people have used the term displacement wave, and I strongly advocate to not use that term. I think a displacement wave, if you really loved that term and wanted to use it, it would be for tsunamis like some of those earthquake tsunamis that Yong showed, where the ocean surface is just literally vertically displaced by an earthquake. The process involved in these largest landslide-generated tsunamis is not one of just a lump of stuff taking up space that would have otherwise been occupied by water. It's actually a momentum and energy transfer process. And it happens especially if a landslide is traveling faster than the wave can get out of the way. So this is basically faster than the shallow water wave speed. This means that as a landslide that is fast relative to the shallow water wave speed, which is faster in deeper water, will transfer more energy, but it's also limited by the amount of energy the water column can contain. So this gives you two different things that mean that the largest tsunamis are going to be in some sort of mid-range depths that are where landslide propagation speeds plausibly could exceed shallow water wave speeds, but there's still enough water to make a big wave. And it turns out fjord depths are often in some of this kind of range where that can be really efficient. You can get a lot of energy from the landslide into the water. And you could think kind of hyperbolically about really tremendous amounts, like if multiple cubic kilometers of Mount Fairweather fell into the North Pacific, I think we could see as much energy as we see in subduction zone earthquakes generated by one of these subaerial landslide tsunamis. Most of the concerns are more local. This is a slope. These bright lines are basically offsets in the slope. This mass could fail into Yale Arm. This is kind of a sibling to the Berry Arm instability, if you're familiar with that one, and threatens some of the same places like Whittier. I'm going to spend just a little time on this particular site. There's two slow landslides above Portage Glacier here, and they threaten a tsunami in Portage Lake. We have a visitor center here. We have all this infrastructure in the area. So when we talk about potential impacts of one of these events, this is a very local area. However, the vulnerability is actually really significant. Conceivably, we could look at hundreds of people at risk, so that's relevant. But we also have two rail lines that connect to both of the major ports in southern Alaska. We have a lot of the fiber optic infrastructure for Alaska. We have a major power line that's critical connectivity between different sections and non-redundant, and we have a number of highways. And so this one event could threaten all of those. And if you really go for especially bad scenario, we could see a sequence of events that would prevent rebuilding. So these could be permanently severed, unlike an earthquake where once it happens, you expect it's probably going to be a while before it happens again. So this will look at those. And we do have some preliminary modeling. This is, I should have labeled this. This is Pat Lynette at University of Southern California's work. It's kind of a mid-range event, and you see it, the wave flooding out of the lake at the low end. The larger end of wave is where we'd really get to those extreme cases. Now, to take this look at the hazard and start translating this into a probability, what we would need is a collection of sites that were meaningfully similar, and we'd want to watch them for a while and see how often they fail. And so I've tried to do that. I've done a lot of mapping in Alaska of slow landslides. These include things that are not very comparable to portage, so you can start trimming this down. These are ones that are moving particularly fast, which would apply to one of the two slow landslides at portage. Still include some things that are very different. If I trim it down just to sites that are next to thinning glaciers and don't have a permafrost influence, we have about 84 sites. 5 of those have failed since 2012. So this is a pretty high failure rate. And you could do really simple math, and you could just say this is something like 0.5% per year. You could get just slightly more sophisticated and take a Bayesian approach, which would give us an uncertainty range. I would say that the problems in the statistics are probably not so much the statistical approach, but that this is a non-stationary probability. You can see if we look at the dates of those 5 events, 2 of them happened last year. That's a pretty remarkable coincidence if it was a random set of 12 years that it would 2 of them would be in the most recent, like basically as I did the analysis. And of course I showed this earlier suggesting we might have a steep increase. So I would argue we should be going, north of 1% with our probabilities in here. We could actually start plotting this out. We could say, okay, there's that uncertainty range from the Bayesian calculation. Somewhere in here would be the probability of that happening if we're plotting up probability versus consequence plotted on the x-axis. And we could talk about what those vulnerabilities are there and start kind of narrowing that block in. And the reason this extends to such a high numbers, up to multiple billions of dollars, is that there is all this infrastructure vulnerability in that area. Now, this is very simplistic. It's treating it as one single possibility. In actuality, smaller events are more likely, larger events are less likely, and you can even get creative and come up with some really crazy, scary events. So if you were to completely line this out, it might look something like this. Now, if you knew the system perfectly, this would be a sharp line, and that would include uncertainty in how the actual event would unfold. But because we have huge epistemological uncertainty, it's actually this big blurry line. And you can reasonably ask, like, how risky is this? How do we think about that? Well, one way of thinking of it is to realize that any diagonal line, all points on that line have equal cost over the long term. So, it's spaced out differently, different magnitudes, those two things balance out. So if you just think in terms of kind of a least cost analysis, it would emphasize stuff kind of in the middle here, where it pushes furthest across this diagonal line. Now, intuitively, I think you might bend this up, because when you get down to these lower probability events, they seem kind of crazy rare. So maybe we can just not worry about that. Let's worry about things that are more likely. Alternately, you could take a robust decision-making approach where you say, well, actually, we really want to put extra emphasis on the worst case scenarios because those are so history-altering catastrophes that we want to really be ready for, even if they are proportional to their cost, less likely. And we can actually look at how different countries have approached this. This is the risk matrix used in Norway. And so they use really a least cost kind of framing, where it's these hard diagonal lines separating different categories. And they would say this is all pretty scary. In Switzerland, they're much more risk tolerant. And you could maybe argue this has that convex up intuitive shape. If I was the one just talking about what's in my head, I would tend to go more in that robust direction. This doesn't matter, right? This is just my own internal culture. And ultimately, these lines here, these curves, those are a cultural artifact. These are basically the risk tolerance of the culture. But if I was representative of the culture, it would look like this. Now, so what do we do in the United States as a whole? Well, we don't actually have any clear statement of what this is. We can look, and I'm almost done here, we can look a little bit at how we've treated some of the subduction zone tsunami risks and just see where those drop in here. 1964 tsunami in hindsight. I actually added this while Yong was talking. I was like, oh, $3 billion. I've got a number now. So this is like, if we assume it's kind of typical of subduction zone tsunamis, it would fall into here. We worry a lot about this. So it would say, maybe we should worry about Portage 2. A lot of work has been done recently on the threat to anchorage from a tsunami, which is not just dependent on the source, but also on the tide. It's very strongly dependent on the tide, which reduces its probability. It's also a more localized area, so that the vulnerabilities are less. And actually, where I live, I've looked pretty closely at the analysis, and they actually focus on an event that I think is extraordinarily low probability because it involves over 5 meters of coseismic subsidence. And so I think that pushes the probability down really low. But we're actually investing resources in these kinds of events, which would suggest maybe it's worth thinking about these as well. Okay, I will stop there. I really appreciate your time. And I think Kristin's going to talk a little bit about what we're trying to do as far as grappling with this kind of emerging hazard.
Thanks, Hig. Very interesting. Wilbur, you have a quick question?
No, I'm clapping.
Oh, okay, good. Let's move on to Kristin.
We're not hearing you, Kristin.
Yeah, just trying to find my unmute button. So yeah, I realize we're almost out of time. So I'm just gonna very briefly share a couple things. So Hig and I, as well as several others, are involved with a newly funded NSF planning grant for 2 years called Arctic TSLP. And the purpose of this planning grant is to really bring together the community. I'm going to skip through that. The Arctic TSLP community and network, and foster new connections, strengthen existing connections. We're also working with a diverse group of stakeholders and rights holders in the Chugach and South Central and Southeast regions to build partnerships for future projects that are really focused on generating a shared understanding of these landslide-generated tsunami hazards. And really, we're trying to facilitate, collaboration and communication that can be the foundation for future projects and actionable solutions. And so this 2-year planning grant is really helping us establish the relationships that can support large and NSF large planning support effort in the future, where multiple NSF projects will be submitted together under one umbrella focused on landslide-generated tsunami related research. So we're putting co-design at the center of our work. And I am just going to share here how you can get connected to the network. So there's a QR code here. I'll also put the link in the chat where you can visit the website. At the website, you can sign up for the email list or join the TSLP network. We're going to be having a series of webinars where folks can connect with each other, and you can learn about research happening in this area across all different disciplines, as well as community perspectives. And watch for our quarterly newsletter and a website relaunch coming soon. And then finally, there's a webinar tomorrow. It's our first webinar, and we'll be focused on introducing the project and providing a bit more discussion into what we outlined and what our goals are. Our second webinar will be a panel with USGS and the state of Alaska DGGS, really focused on how this TSLP effort and NSF-funded research can complement the state and federal research happening here in Alaska. So sorry to breeze through these. I will put the links into the chat, and I'll just stop there in case there's any time for questions or discussions before everybody signs off.
Thanks, Kristin. Very interesting. And we still have a few minutes. Do you guys have any questions? And I'm willing to stay a little longer beyond the top of the hour.
Yeah, I'm okay to stay a little longer too.
Mm.
Kristin, I like that little photo you used next to one of yours in Byron Creek. You're in that picture. You're standing on one of the green blobs. It's a mapped on instability. Hopefully, not too dangerous one.
I have tons of questions, but we are running out of time. I might have brought this up before, but I'm interested. So this is an NSF initiative, the TSLP, Kristin. To what extent would it? So USGS is probably involved in it as well in some way or another. So to what extent are other laboratories, maybe, or agencies involved in that? Maybe DOE in particular. That's the one that I'm representing here, I suppose. Can you comment on that?
Yeah, so at the core of the project, the key partners or co-Is involve, so myself here at UAF, Anna at Woodwell Climate Research Center, HIG, and then we're working closely with the Chugach Regional Resources Commission, which is a regional tribal organization for the Chugach region. So that's who's involved in this specific planning grant. But one of our key goals is just that, we are putting intentional effort into trying to build and grow this network. So the TSLP network is not new. People have been connecting and having webinars and conversations for quite some time. But our goal is to look at how we can build and grow and diversify that network. Specifically, I'm really interested in how we grow that network into involving more social scientists who can do this work. But yeah, so as you'll see, as we kind of build out the website and the webinars, the goal is to really kind of bring in folks from different perspectives. So I could imagine, potentially having somebody from a variety of different agencies present, or having people connect with each other, because it's going to be all about finding, folks who want to potentially work with each other to address some of these big questions related to this area of work.
I would just add one structural detail. So this is through NSF's large project support model, which I don't think has been explored a lot at this point. I haven't actually talked to anyone who's gone further through the process. And that means that the outcome of the planning grant is a set of NSF proposals, and it's totally open door to anyone who wants to join the conversation of figuring out what those proposals will be, and definitely looking towards people, to lead different proposals within that. So this is definitely not at all a closed group, both on the community end of trying to connect with stakeholders, and also on the academic end of trying to bring in the full breadth of possibilities from the academic world.
Yeah, great. I mean, I don't know how advanced the modeling capabilities are for these kind of things. I mean, Yong showed incredible animations, and it was fantastic. I mean, here at the, let's say, Los Alamos National Lab, there's a lot of computational capability for anything that blows up or that creates shockwaves and stuff like that. I'm just wondering if there is anything that our lab could bring to bear to that. And we also have ocean modeling capabilities and things like that. Maybe it's a pipe dream for me to be involved in this.
Yeah, that's great to hear. Would like to collaborate with anyone. I think most of the Vasily is also on this talk because we are mostly working with some people from Los Alamos to explore modeling of asteroid impact. Especially recently, there's like 1% probability that one of the asteroid will hit Earth in 2032. I think Vasily just got back from some meeting talking about how to prepare for that. Yeah,
that's actually 2% now.
Yeah, 2%. Yeah.
It's changing fast. I would say as far as where the modeling is, there's still some pretty big discrepancies between different things, and we don't have nearly the track record of case study matches, like where we really have great records. And part of that is that a lot of these past events have been localized, where the only tide gauge records are very, very distal. And there's some really significant evolution that happens from that source area. And so then what we have is just limit of inundation. And you can kind of fit a limit of inundation in more ways. Pat Lynette and Katie Barnhart are really actively, they've taken quite different approaches to modeling some events that have happened and some events that are of concern. And so they're trying to organize a workshop. I'm not sure exactly what the current, maybe Yong or Vasily knows.
Yeah, it's going to happen in 2 weeks.
Oh, really? It's that soon? Well, so getting involved in that would be it's a pretty short fuse. But I'm very curious to see what the outcome of that is, and that's going to be a kind of a benchmarking sort of process.
Yeah.
Perfect.
Yeah. Thanks, everyone, again. I mean, Alaska is a remote region, right? I mean, there are lots of events, but it, kind of scattered. I guess your probability distribution and the damage kind of estimate those pictures looks so interesting to me. How do people address those potential risks in the most sort of efficient way?
Yeah, when we were first looking at hazard from Barry Arm, the National Tsunami Warning Center was very hesitant to get involved because they said, well, we deal with the big events, right? And I don't know, this is some more localized thing. Because of there are a few reasons that although these are usually localized, I mentioned briefly, we need to think about circum-Pacific events as well, and circum-Atlantic, looking at like Vigot Strait. But mostly we're talking about localized events. They can be really high impact, and there are fairly plausible scenarios where the death toll could exceed any natural disaster that the U.S. has ever experienced, where the impacts could be, tens or more billions of dollars, especially given the potential to sever really critical infrastructure in ways that can't necessarily be rebuilt. One of the things we see in many cases, how universal this is not something that I think anyone has really pinned down, but in many cases, a big landslide is part of a sequence of big landslides. And this really changes the nature of that hazard because, generally if something bad happens, we might think, all right, so now let's put our energy into rebuilding. But if you have a situation where you're like, well, we have to wait, a month because we think the probability is extremely elevated in that first month of another event. And then we maybe should wait a year because the probability is still quite elevated through that time. And then we should probably wait a decade because, you run into the situation where recovery is really cut off. And I think this is an important question that there's a lot of different tacks to really approach it, but it's one that we haven't really tackled yet.
Could I pop into the conversation here?
Sure. Go ahead.
To Hig, I'm an ex-building inspector, retired many years, and I've recently become much more interested in wave energy management. And I'd be interested to have some discussions with you about your modeling of the waves from the landslides coming down into the water, and also discussion about hazards. So if that would be possible, that would be really appreciated.
Well, definitely drop me an email. I'm not the modeling pro in this story, but I can definitely talk about the hazard and you know, I keep close tabs on the modeling efforts there. Yeah, definitely interested to have the conversation. One little thread that came up with the portage hazards, that there's this visitor center run by the Forest Service that's right in an area that's really vulnerable. And when the Forest Service was first kind of trying to grapple with this this hazard that they hadn't realized was there, one of their questions was, is there some room that we could all go into in the building to be safe from the tsunamis? So like, can we go hide in the bathroom? And I don't think that's a good strategy. So but yeah, it would be good to talk.
Where would I find your email?
I'll put it in the chat.
Well, thank you.
Great. Yeah, this is super interesting talks, and I'm glad people are connecting here also. Yeah, take a moment to register the emails and contact informations, and then hopefully this will also be posted on the IRPIC webpage when the page is back, so we can look back. I do mean to look back into some of the details here. Thank you again, and I hope you will enjoy the rest of your day. See you later.
Thank you all.
Very much.
Thank you.
Really, really interesting. Thanks.
Bye-bye.
Thank you.
Thanks.
Thank you very much. Enjoyed it.